slide is that when we are talking about faults, we need to understand which stress regime are we in. So by stress regime, I mean that whenever we at different part on this earth, we have something called, so for people who are not from geology background, we have something called plates or plate tectonics. So what happens is that we have number of plates which are on mantle, and they are basically either subducting or colliding with each other. And these are the primary reasons of stresses which are formed on the surface, on the Earth's surfaces, and this leads to generation of faults. So over here, if you look at the left picture, it shows you tensional stress, compressional stress, and shear stress. Now, if I can take your attention to the right picture, which is and to the point B, you can look at the directions, which are primary directions are sigma 1, sigma 2, sigma 3. Now, if you now look at the tensional stress, and if you look at the normal fault, you can basically have an idea when there is a tensional stress, the sigma 1 fault is acting on the top, right? Similarly, when you are looking at the compressional stress, you will be having a thrust fault. And when you are looking at the strike slip fault, you are going to have shear stress. The main reason I am starting to give you an idea of this kind of fault is because fractures are all associated with the faults. So until and unless you are having an idea how faults are, then the idea of fracture becomes a bit alien, and I won't be doing injustice to this whole presentation. Just to complete this slide, so you can also have an idea looking at the figure on the right with A revenant, the mode 1, mode 2, mode 3, which is also can be related to tensional stress, compressional stress, and the shear stress. And you can have an idea where the opening is happening, the sliding is happening, and where the tearing can be happening. Now, moving forward, in the left-hand part of the slide, I have tried to capture the different fall zones. The fall zones are, if you look closely to this map, it is also showing you the arrow. For example, if my mouse is available over here, you can see in the Indian Ocean side, if you see at the Owen transform fault, so the particular fault type is having an orientation or movement towards north-south. Now, those of you who have done field geology, specifically you have gone to any structural field work, you might be remembering this particular kind of stereo nets, where your professor used to tell you, go with your clinometer and the dip, and you measure the dip and stuff, and then you plot it. Now, the fact is that why I am telling you this particular information, why it is very much needed. Now, we have to understand that when we are looking at fractures, we have to know what is the orientation of this particular fracture in any area. And to have the right kind of understanding, we have to understand the regional tectonics, where you have the either you are in a normal thrust zone or a shear zone, or whatever the stress regime is it, but also in which direction the stress regime is. Because at the end of the day, if the if the fractures orientation in that particular region of interest is in northeast southwest, and if we are trying to delineate northwest southeast fracture, that is not going to make any sense to us in terms of economics and in terms of modeling or in terms of delineating it, which will have impact in later on. Now, if you have know what if you understand what this particular FMI looks like, so I think so most of you who are in oil and gas business have heard the word FMI, which are nothing but the image logs of the subsurface holes. Over here, if you look at the after the in the picture in dip orientation, you have something called tadpole plots. So the head and the small sticks over here basically is giving you the direction in which the fractures are oriented, or the bed boundary or the sedimentary drips are. You can also form a borehole geologist who does that will give you more information. He will be giving you information about the in situ fracture, induced fracture, etc., 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 which are very much important to understand not only the stress regime of the whole area, but also of that particular block or fault block, because it might happen due to certain interaction or certain geological situation. That particular block might not have the complete alignment or orientation of the fractures in the direction of the major fault direction. Now, the most important thing. So if you now just, I would like to recall you the 3 slides back. So what I have done, I have talked about what faults are, because the fractures are basically associated with fault. Then I have talked about the next important thing is the orientation of the faults and the fractures in starting from a regional scale to a borehole scale. Next important thing which you need to understand is that whether the fractures which we are looking in a borehole are open or closed. And the only way to understand and have hard evidence about those fractures comes from borehole images. To look at, if you look at the image on right, the image on right is indicating a high conductive fracture, whereas the image on left is trying to show you a high resistive fracture. And for the sake, I have used a field representation, how it might look in the field. So till now, I have set the tone from faults to fractures to orientation and whether those fractures are open or closed. Now I will take a leap. Whenever we are talking about fractures, 2 things comes up: the matrix and the fractures. In MENA region, when we are specifically in carbonate environment, normally there is a conversation whether which is the dominant producers, whether it is getting produced from the matrix or it is getting produced from the fractures. And normally it is seen that the major production which happens is from the fractures compared to matrix. Now, why is this particular slide important? If we are from a geologist or even from a geophysics or a geomodeler standpoint of parent, we need to understand what kind of facies, carbonate facies are we, and depending on the type of carbonate facies, what kind of production unit which can look up. So in the right, it typically makes a plot of porosity with permeability, and it has delineated type 1, type 2, type 3, type 4, depending on. So the extreme right, type 1 is fracture dominated, where there is high porosity and permeability, whereas the type 4 is your matrix dominated, where you have low permeability and porosity. Now, if you try to understand and map this particular picture on from left to right, you can understand that. Let's say you are in a moldy grainstone where amount of leaching has happened. Then this can typically, you will be saying that if you are producing from an environment which is dominated by moldy grainstone, you will be having a type 2 kind of a facies or a lithofacies, which will be more the flow will be more dominated from fracture compared to matrix. Similarly, if you look at a grainstone or a vagi dolomite vacay stone, where, as we know, the diameters are declining, you can say the production will be more controlled by from the matrix. The contribution of the production will be more from the matrix compared to fractures. So this is also very important when we are trying to understand fractures, when we are trying to understand fracture and trying to do modeling, that what kind of lithology what kind of carbonate division are we in, and what can be the contributing factor in this particular case. So a small before going to the next slide, a small recap of the continuation of this particular PPT, and what I'm trying to establish is that we are in the MENA region, which is mostly the production. Major oil and gas production is coming from carbonate, and these carbonates are having production mostly from matrix or from fractures. And when we are talking about fractures, the major understanding is the orientation of the fractures, which we have an idea mostly from the regional fault orientation, and most important, whether those whether those fractures are open or closed, which we have an idea, which we get the hard fact from FMI images. Now, moving on, the next question is that how do we locate those fractures? In the modern, like for last 30-40 years, what we see, the globally all over the industry, our North Star is acquiring seismic and using different surface and volume attributes to understand different parameters. So the major important parameters or the volume attributes which we use are curvature, coherence, variance, and tracking. So over here, I will take a small pause and I will ask you to look at the image on the left top. If you look there, there is a plot of high and low amplitude in terms of seismic, and there is and in the left there is called curvature. So this particular image at the extreme left, you can see there are red and blue. So if you look at the color scale, so what red is showing, the high red is your positive curvature, and the blue is called negative curvature. And for more understanding, the black line is nothing else but the well track. So your next question will be, so what are we what you want to imply? So what you are actually looking is that this particular well has been drilled through a sinkhole where the reds is showing the mouth or the top of the sinkhole, which is having a positive curvature, whereas the blue is the inside the sinkhole, which basically shows a negative curvature. Moving on, the other attributes which we mainly talk about or we use are ant tracking, which is one of the most favorite and has been used, and I think so had been it's an IP by 𝗠𝗱𝗰𝗁𝗁, which has been used widely in the industry throughout for last 15-20 years. Now, I would slow down and try to make you understand so over here my next approach will be to make you understand the basic geophysics of how this curvature attribute actually works. So curvature is basically the differential of or the reciprocal of radius. And if you can imagine a particular circle, and if at the circumference, if you can take a derivative. So let's say we have a small arc on the circle, and that particular small arc makes a degree of W, and the radius is R. So curvature and the radius is S. So the curvature is nothing but the derivative of dW by ds. So for people who for people like me, basically from geology background, who don't have a understanding of grip of major geophysics. So for us, we can understand that curvature is nothing but an inverse of radius. Now, how it becomes relevant to us? So if you look at the picture just next to you, you will see that if you are in a anticlinal settings, you are going to get positive curvature, where you are in a syncline kind of a setting, you are going to get negative curvature. Now, I will again go back to this slide. Now, I think so from this information which you have got, if you now look at this particular sinkhole kind of a situation, now you can appreciate why at the mouth of the sinkhole you are getting a positive curvature, whereas inside the sinkhole you are getting a negative curvature. I will just pause for some time to basically for you guys to visualize the thing, why it is happening. Okay. Now, if I'm going to take your attention to a more case study, which is from Calgary. So if you look on the right, the same curvatures are plotted along a surface, and what you are basically seeing is the blue over here is the negative and the red over here is positive. And this is basically the time slice is on the vertical, and laterally or horizontally what you are seeing is a display in form of a chair structure. And this particular red and blue are basically delineating the faults which are present but which are not very much visible in the seismic. So the other thing is that when you are interpreting seismic, sometimes because of the quality of processing or quality of acquisition, the fault might not, the continuity of the fault or the fractures might have a limitation. But by using this particular attributes like coherence, curvature, or ant tracking, the continuity of that particular fault or fractures becomes easier to delineate or to understand. To make the understanding more clear, I think so over here, if you look, you can understand more. So on the top in the picture A, what you're looking is a coherence slide over here. And these are the curvature slides. So there is also a play over here when you are doing curvature analysis of long wavelength and short wavelength. The long and the short wavelength had its own pros and cons, which are basically the sum is used for delineating small scale delineation of a facies. The other is basically understanding the delineation of faults and fractures. So in nutshell, what I want to say is that there are when you are in a post-stack environment, there are number of tools which can be used to delineate fault and fractures. But it is you who have to keep on trying and playing with the different values and the softwares to actually have some meaningful information which will be put later on in your model. Now, moving forward, but a small caveat from this side is that, as we know, when you are in post-stack seismic environment, what happens is that the post-stack seismic is mostly processed in a way where your major emphasis is for horizon interpretation. What happens is that when your emphasis becomes horizon interpretation, there are number of information like the geophysicists will be the far angle information or which are relevant are lost. So the other way or the other more advanced way of fracture identification is through understanding and using different pre-stack methods to do so. In one of the so if you go through literature, you will be finding different pre-stack methods. For one of it is the azimuthal Young's modulus eclipse fitting on OVT data, where OVT is a kind of vertical traces of particular far angle azimuths. So what does it does that in a particular stack of a pre-stack, they do the inversion to generate rock physics or basically petrophysical parameters like bulk modulus, Young's modulus. And after doing that, they use an algorithm called eclipse fitting to understand the orientation and the intensity of fractures. The other methods which are widely used is pre-stack inversion to do geomechanical rock properties. So what mainly happens is that in far angle stacks, the information relevant to fractures remains stored. That's the assumption, and the behavior of Young's model, the values of properties like attributes like geomechanical attributes like Young's modulus and bulk modulus in a brittle rock by means the rocks which tend to have fractures is different from a ductile rock. So that particular philosophy or information is used to delineate fractures by doing pre-stack inversion by doing pre-stack inversion. There is new methods like amplitude variation with angle and azimuths, which are now become quite famous. So over here, I am showing you a particular case study which is done in Vudahi field. Hope I am pronouncing it correctly. So if you look over here, so they are trying to process. They are trying to use pre-stack data. While doing so, what they found is that in the north-south direction, in the same in the same particular stack, the velocity is quite high. So if you look at the velocity is quite low. The velocity has become slower, whereas these in the same location in east-west direction, they have found the velocity is quite high. So what, for a geologist or a geomodeler, the take-home message from this slide is that depending on the orientation of the fracture, the velocity do change in post-stack in pre-stack domains, and that is what is getting reflected. So in this paper, if you explore, you will be finding is that the east-west is the major stress direction, whereas the major orientations of the fracture are in north and south. So that's why this particular velocity anomaly has been found. Now, I will take a pause and try to accumulate what we have been discussing so far. So what we have done is that we have covered the understanding of what fault and fracture is. We have talked about the orientation of fractures. We have talked about the necessity of why we need open fractures. Then we jumped into the seismic domain. Obviously, we have touched and talked about the different lithologies which are associated with carbonate and the importance of your fracture, fractures, open fracture and closed fracture. And then we have jumped into the post-stack domain, which we have touched upon some of the relevant volume attributes which are used to delineate discontinuity. In this time, it can be fault on fractures. Then, as we know, there is limitation in post-stack data. Then we are touched the pre-stack domain and the different algorithms and methodologies which normally are used for delineating fracture. So in this stage, what we understand is that we have reached where we have got an overview where we have deciphered the orientation of the fractures from the seismic, and we have cross-checked that particular orientation, whether it is closed or open, using the FMI data, which is normally done while you are after your triple combo log collection. Now, what I'm going to talk about is I'm going to talk about a case study from Ilam and Sarbakh formation from southwest Iran. So the case study gives an holistic idea about how all the information, starting from the well level information, structural information. By structure, I mean fault and horizon, and then the attribute information, and how you take all this information to create a DFN model, and then how you predict that. So what you do is basically, as I had mentioned previously, in well level study, you study the image log, which gives you the fracture types, density, the aperture length. Then you basically determine the horizontal stress direction, and obviously the sedimentary units, etc. Now, in the seismic domain, after you have done your basic seismic and horizon modeling, and then using the well information, you have done your velocity modeling, which normally seismic is in time domain. You use velocity modeling to convert the time domain data to depth domain, and after the depth domain, you create a structural grid. By structural grid, I mean you basically create a framework where all your interpreted faults and horizon are inside a 3D structure. Once that structure is ready, what you can do is that the attribute, after you have completed your attribute analysis, you are more or less sure from the attribute which way and what are portion of those volume attributes are talking about or delineating in that particular seismic volume or the attribute volume, which can be taken inside the structural framework. Now, what you do is that you populate those particular information inside your model using different geomodeling algorithms. So I will slowly go through and try to explain. It's a very nice and very, I won't be using the word simple, but very easy to understand case study for a beginner's point of view to do how fracture modeling can be done and using all the information. So over here, after, as I mentioned, after doing the interpretation and velocity modeling, they have created a grid for different formation. And after creating the grid, they have populated their permeability and porosity using a particular attribute. Then what they have done is that there is something called fracture intensity. Fracture intensity is nothing but number of fracture in a given area, and that is computed in an FMI. And you can basically have discrete logs of that particular fraction intensity, and they have then used that particular fracture intensity and upscaled that particular information in the model and populated it. So you can see that the in the image over here with porosity, the fracture intensity and the porosity actually talks with each other, and it is the same with over here with permeability as well as intensity. So the point over here I'm trying to make is that, so this particular intensity log can be not only used, not only has been helpful over here to understand which formation over here, because if you see there are two formations, Elam and Sarvak, which one is producing more, but it can also help you, it can also help you to basically give you as location if you are in an appraisal phase or a development phase. Now I would like to make my concluding remarks for this particular presentation. All the models which a geomodeler are make has to be obviously handed over to the RE and production guys who are going to do history match. And as we have seen, there are always an issue, and in a setting like fracture, which is very much complicated, there are stuffs like dual porosity and permeability population which comes up, and it becomes a to and fro process to mimic the nature, the subsurface nature, to the most reliable which can be done using the limited information. So I would conclude is that all your models has to be validated with all or whatever production data you have. It can if you are in exploration phase, it can be a well test data. If you are in production, if your field is producing, you have relevant more data, but your model has to be QC'd or it validates the production data. So I would like to emphasize from Mr. George is that what I understand that all models are wrong, but some models are useful. So I think so with my limited knowledge, what I have understood that our focus should be as a geomodeler, as a geologist, is to build useful models. Thank you so much.
Thank you, Mr. Abhinav. We have two questions in the chat session that maybe you could answer, please.
Yes, please. What if you do? I think so I have answered that. What if we do not have access to pre-stack data? If we do not have access to pre-stack data, What if we do not have, if we do not have access, then we have to satisfy ourselves and use the post-track data and use whatever information we have. And why fracture intensity, not fracture density in element survey formation? See, it's a very nice question in terms of fracture. So over here, what I have understood from the paper, the fracture intensity showed a positive correlation with the attribute which they have used to populate the model. Normally, I have seen fracture density being used, but over here, my understanding is that, so that's what I was saying, that you need to be very robust about what data you're using and which data is actually speaking to your future seismic, if you are planning to use seismic in your model. Hope that answers your question.
Okay, I don't know if we have another question. Yes, Joseph, if you want, you can open your microphone. You can now make the question.
Italian.
Yes,
Yes,
we can
Joseph.
hear you.
So, about the last statement that you made by 𝗏𝗰𝗰𝗂𝗏𝗃, that all models are long, but some are useful. Like, I want to understand, like, I don't get that Italian. So, if you can explain.
Joseph, you are not audible. Can you type your question in the chat box? You're not properly audible. I couldn't understand your question.
Okay, so while Joseph makes the question, somebody also asked, can we look for fracture clustering from seismic data?
What exactly do you mean by fracture clustering? If you can mean, like, you are looking at the orientation, you're looking at the, like, whether the fracture are forming a closed network, open network, connected network. Yes, why not? And I think so. Geophysicists can, if there is any geophysicist, can shed you a more light to that. Okay. Joseph, by that, so it was more of an learning experience which I had. I wanted to say is that there is nothing called a perfect model. It changes with time as you get more information, as the field matures, more information comes in, your models, you update that model. So there is nothing called a right or wrong model. You need to have a model which is robust enough, which serves the purpose of the reservoir engineer or the simulation. Hope you hope I make that is clear.
Yes. Thank you very much.
Okay, so if we don't have more questions, there's a comment.
Maximum data integration at times make more robust and usable. Yes, Shahan, completely agree with you, if I'm pronouncing your name correctly.
Great. Great. So thank you all for attending today's webinar. It was a pleasure having you with us. Special thanks to Mr. Mukherjee for sharing your expertise and for this wonderful webinar. If you couldn't join us live, the recording will be available soon and we'll be sharing the link shortly. We truly appreciate your participation and look forward to seeing you in future sessions. Thank you and have a good day and have a good night.
Thank you, everybody. Bye.
Thank you. Bye-bye.
Thank you.